Welcome to the presentation of wide-range MRI artifact removal with transformers. My name is Lennart van der Goten, and this is work that we have been done at KTH, Royal Institute of Technology and SciLife Lab, Stockholm. What is this paper about? This paper is about artifact removal. Artifact removal is a highly relevant topic within radiology. For instance, for MRI scans, people are assumed to lie still in an MRI tube, and whenever they move, it causes the scans to become unusable. Redoing the scans is often expensive and always unpleasant for the patient. Retroactive artifact removal tries to remove these artifacts afterwards. Therefore, our goal is to take these artifact-effective images and synthesize artifact-free counterparts. Transformers have become a staple already some time ago within the NLP community, and they have been shown to work also very well within the computer vision community. This has started with vision transformers, which are commonly referred to as VITs, and it has continued with SWIN transformers. These architectures can be extended to dense predictions, as has been done with SWIN IR, so they also work within these scenarios. MRI images can easily be conceptualized as 3D images, and because of this additional spatial dimension, model efficiency is absolutely crucial. Our goal is to design a transformer-based architecture that can filter out a wide variety of artifacts while still being efficient. Let's jump to the problem formulation. So as I said, we conceptualize MR scans as three-dimensional images of some given resolution. So we use 128 and 256 depending on the voxel size. We have two key assumptions. First of all, we assume that there is a highly curated data set with minimal artifacts. Secondly, we assume that we have a high-fidelity artifact simulator that can synthesize a wide range of these artifacts that are also highly realistic. We use this artifact simulator on the artifact-free images to get images with artifacts, and then we let the neural network learn the inverse process. Often these artifacts are not local, and this necessitates that our neural network can process this global information as well. Let's go to the related work. So obviously there has been a lot of work on inverse problems. So one of these papers is DeBlurGAN, which suggests a conditional GAN for image deblurring, but there are also other works that tackle denoising, super resolution, etc. Within the MRI domain, you have Tamer, which assumes that patient motion is rigid, and when you do this, you can solve the equations to remove this degradation from the images. Duncan is a work that is very similar to ours. They are inspired by CycleGAN, and they define an artifact-free and an artifact-affected domain and translate between these two domains. This work is, however, slice-based and undoes 3 artifacts. Saragan is synthesizing full MRI scans from undersampled scans, and these undersampled scans are often cheaper to get, and they also don't take as long. So this is why this is an interesting task as well. We have a couple of architectural considerations. So VITs, as I said before, have proven that transformers can be easily applied within the computer vision domain and can obtain very good performances. The SWIN transformer has continued this work. And the idea is that you divide the image into a non-overlapping windows, and then the attention is only computed within these windows. If you do this, however, then you have no window-to-window communication, and therefore you need to have a second attention type, which is called the shifted window attention. And when you do this and iterate it, you get increasing context sizes. Our idea is to supplant the second attention mechanism with an attention mechanism that is global right away. So after one application, all the global information can be processed. Here you see an illustration of our architecture. So on the top left you have the image with artifacts, which is divided into patches. These patches are then flattened out and given to the residual chord chain, which is also depicted below for more detail. And in order to reverse these structural changes to the tensor, we also do the inverse path to ultimately get a three-dimensional image. We use the G2L function that we have defined as like this. So assume you have an input matrix C, which is color coded to help understanding, and then the G2L function is using window sizes. So we use 2 by 2 here. So we partition the input matrix C into 2 by 2 windows or patches. And then, for instance, the elements 0, 2, 4, and 6 are all at the same position within their window, and therefore they get contracted in the result. This operation is fully invertible, as you can see in the right column. Here we have an overview of the 3 attention type we have already talked about. So on the left, on the center, you have the attention mechanisms used by SWIN. So the first one is WMSA, which is defining the windows to be adjacent elements, and then you have the shifted window approach, SWMSA, which enables adjacent windows to communicate. Our approach, G2L MSA, is grouping the global information into a local context, which can then be easily processed with a WMSA afterwards. We have done a couple of experiments to show how well our method performs. We used Torch.io, which is an MRI artifact simulator, and we decided to synthesize 8 different artifact types. We apply each of these artifacts with a probability of 1 divided by 8, and therefore it can happen that multiple artifacts are active on an image. We compare our method to established methods such as ResNet, DenseNet, VNet, CycleGAN, and BicycleGAN. In order to enable a fair comparison, we scale up the model size to fully utilize the memory of an RTX 3090. We also established an ablation which we call WSW-MSA-ART, which is using the attention mechanisms of the SWIN transformer, but within a 3D context. Here you see some qualitative results, and here you can also see that our method is doing extraordinarily well at reversing these artifacts. Let's jump to the quantitative results. So we have calculated PSNR scores between the artifact-free images and the reconstructions from the artifact effective images, and we see that our methods outperforms the others. We also considered a brain segmentation task and have shown that our method improves the quality of the brain segmentations. Let's go to the conclusion. Our experiments have shown that our method, WG2L-ART, is able to reverse 8 artifact types that often occur in practice. We have shown that the PSNR and the SSIM score of our methods are very good. Furthermore, we have shown that our method works for a brain segmentation scenario that is often found in practice. Future work will include different MRI modalities and also CT scans. Thank you very much for your attention.